All right, great. So welcome to everybody who is out there in the world watching on YouTube. This is the first virtual edition of UMass Systems Lunch. So we've been running UMass Systems Lunch for about 13 years, which seems crazy. So it's all grown up. It's a teenager. Time to go be off in its own room and talk to people on the internet, I guess, as teenagers do. So we're delighted to have our first speaker today, who's going to give us a great talk, Adrian Sampson. So Adrian is a faculty member at Cornell University, where he's an assistant professor in the CS department. Adrian works on programming languages, computer architecture, and the abstractions that separate them, which are unfortunately huge, and Adrian will be talking about how we can bridge them. He previously worked on approximate computing, which is the idea that we should allow machines to expose errors to some kinds of applications as a trade-off for computational efficiency. He sees approximate computing as an instance of a broader breakdown of airtight distinctions between hardware and software concerns. And we are ready to listen to Adrian talk to us about how we can bridge that abstraction gap. So with that, Adrian, please take it away.
Awesome, thanks very much. Am I both visible and audible at this point?
You are good.
Great, awesome, thanks. I am thrilled to be here in Amherst today. Amherst is a beautiful town. I have already been made fun of once on Twitter for calling it Western Mass, a debate that I admit I don't completely understand. Anyway, I am absolutely thrilled to be talking about some of our work that we're doing on programming languages and compilers and stuff for generating custom hardware. I do want to just really briefly acknowledge that for those of us in the US, today is like an extremely bonkers news day. And if you're like me, you are like having trouble not constantly refreshing Twitter. I personally will not be refreshing Twitter during the next 45 minutes. And if you want to, you can take that as a challenge to not do that as well. I'll try to make this as interesting as possible to hold your attention away from the burning world. Anyway, further preliminaries are that I also want to acknowledge that all of the work that I'm going to be talking about here is shamelessly taking credit from a bunch of excellent researchers who are in our lab. There's more than I could fit on this slide, even in names, but here are a few sampling of the researchers who worked on some of the stuff that I'll be talking about today. If you want to learn more about the research or more about the people who are involved in the research, this is the URL for our lab website. It's capra.cs.cornell.edu, where you can learn all about these projects, find links to papers, and all of that. The provocative thesis of this talk is that reconfigurable hardware, that is, things like FPGAs, have been for too long dominated by computer architects and have not seen enough attention from programming languages people. Reconfigurable hardware, like FPGAs, is super exciting, has a lot of potential to like break through performance barriers that have lasted for decades for general purpose hardware. However, the way that we think about FPGAs is dominated by a view from hardware folks, and that is fine. It's served us really well up until this point. But I think we need to bring this into further balance and bring in ideas from the programming languages and compilers community that is even conventional wisdom in software to make the story for programming these things, for actually programming this programmable hardware a lot better. To frame this problem, I first want to ask the question, what even is an FPGA? If you've never heard of FPGAs, you can take this time to furiously Google it now. But if you do know what an FPGA is, I'd like you to formulate in your mind just a one-sentence answer to the question about what an FPGA is in a sort of philosophical sense. What is it doing? Ordinarily, I would ask people to like break, if we were in person, I would ask people to break in with interesting answers. People will say that it's a reconfigurable circuit, or it's just a bag of gates that you can wire up in any way you like. And this is a reasonable way of thinking about it. That is, it's a way to like construct any circuit you want without actually physically constructing a circuit, which sounds sort of like a contradiction, but that is the traditional way to think about FPGAs. I want to point out, though, that is only one way to think about FPGAs. It's the traditional way to think of them as sort of malleable circuits, in particular as a kind of hardware that's good at emulating real circuits. And the reason that you use an FPGA in this traditional sense is as a stand-in that is sort of cheaper to get than an actual special purpose circuit that you manufacture for a single purpose. Here's a kind of like cartoon diagram that's meant to convey this. If you have like very low volume, it doesn't make sense to pay the enormous cost, the startup cost for manufacturing an ASIC. So you might as well buy an FPGA, which is a lot cheaper until you get to massive scales. This is the traditional use of FPGAs, and it is, to be perfectly honest, the majority of use cases for FPGAs today. Things like embedded devices, for example, have a lot of FPGAs in them for this purpose. That is for sort of small volume and other use cases where it doesn't make sense to tape out an ASIC, but what you really want is a circuit. That is distinct from an emerging use of FPGAs that you may also have heard of, which is using FPGAs as a general purpose computational accelerator. That is, as something akin to a GPU that is good at executing certain kinds of programs, bad at executing others, but in any case can get you huge 100-fold efficiency gains over a CPU if you are willing to put in the somewhat exotic programming effort in order to make it do what you want. This is fundamentally different from the traditional view of FPGAs because the fact that it's emulating a circuit is completely immaterial. All that matters is that we're taking a computation that fits into a certain kind of pattern, and we're making that computation far more efficient by using hardware that's customized for that sort of a domain. This unlocks a whole new set of applications for FPGAs that people are really excited about right now. Things all the way from like machine learning to scientific computing are all like sort of on the table as applications of exciting FPGA hardware. And this talk is about that latter segment that I think, again, to be frank, is still a minority of the uses of FPGAs, but is where a lot of the potential is in the future, and what makes me excited as a computer scientist. This view of FPGAs as computational accelerators is the thing that you have heard of, for example, underlying the great successes at Microsoft in using FPGAs in data centers to accelerate both search and machine learning. And it's also, entertainingly, what Apple will sell you. Apple will now sell you an FPGA. They're selling it as an accelerator for video editing workloads, but it is an FPGA card wrapped in fancy black plastic that you can put into your Mac Pro. So in this view of FPGAs as computational accelerators, there is a really strong analogy to GPUs. GPUs, of course, used to be graphics processing units. They used to be things that were exclusively used for graphics until it was realized that like there's an underlying computational pattern that they're good at, that they can expand, so they can expand beyond that sort of limited domain and accelerate anything that is data parallel and fits their SIMD execution model. FPGAs, I think, are entering a similar inflection point where they used to be for circuit emulation, and now they're for some ineffable broader class of computations. This brings up a really interesting question, which is what this talk is about, which is what is the appropriate programming model for the more general purpose view of FPGAs? GPUs, of course, have grown a lot of useful general purpose programming models that expose what GPUs are good at. So what is the right programming model to expose what FPGAs are good at? Let's look at the status quo for how to program FPGAs. The kind of gold standard for programming FPGAs is the same sort of tools that you use to design custom silicon. If you've ever seen Verilog or the modern equivalents like Chisel, these are all register transfer level or RTL languages. They're hardware description languages that sort of give you direct control over the gates and wires that you're constructing your hardware out of. And these, for good reason, these same tools are repurposed for FPGAs. And this is what is behind those successes I showed a few slides ago. For example, the acceleration in Microsoft's cloud is based on programming at the register transfer level. The problem, of course, with using RTL is that it's extremely low level. That is, like, it's not the way that we're going to like open up the potential of FPGAs to everyday people. This is a really problematic analogy, but I'm going to make it anyway, which is that RTL is kind of the assembly of FPGAs. That is, it really feels like you are directly controlling the computation in a very low level way, which is like super critical for a very rare set of use cases, but is too low level for most mainstream programmers, even when performance is everything but a 99th percentile concern. So of course, in the CPU world, we have higher level abstractions. We have things like C, which is not an inordinately abstract language, but does give you a lot of productivity without sacrificing the control over the efficiency of the CPU. So it's natural to ask, what is an analogous language that raises the level of abstraction above RTL without sacrificing total control, but still makes things a lot easier to program than the equivalent of assembly? Surprisingly, the answer from the hardware side exists, and it is C. That is, there are a lot of tools called high-level synthesis tools that are compilers that translate from C into RTL. To be blunt, I think this is not the way to go. And it's somewhat surprising that this is the way that the industry has so far filled in this analogy. That is, the thing that we use to program FPGAs is a legacy software language. Sometimes it's C++, sometimes it's even OpenCL. But in any case, these are languages that were invented to target GPUs or CPUs, not to target FPGAs. To put it differently, I'm going to pick on this sentence that I found from an HLS paper, and the authors will remain nameless because I think this is overall a good paper, but I cannot resist picking on this particular sentence. I think it's such a remarkable sentence that I will read it out loud. It says, since RTL programming in VHDL or Verilog is unacceptable to most application software developers, so far so good, it is essential to provide a highly automated compilation synthesis flow from C++ to FPGAs. And here I start to disagree. That is, to summarize, I think that the premise is true, but the conclusion is false. That is, I think we need to do better than Verilog, but the right thing to do is not to adopt a legacy software language and port it over to FPGAs. In particular, I think this is the situation that we get into when we let architects run the world. That is, the correct way to, the most productive way that I can think of to use FPGAs effectively relies on an equal balance between ideas from programming languages and compilers and ideas from the hardware side. And right now, the ideas from the hardware side are drowning out the ideas from traditional compilers. In our lab, we see an opportunity to reinvent the entire system stack for reconfigurable computing, all the way from high-level languages down to the lower-level abstractions and targeting FPGA hardware eventually. In this talk, I'm going to tell you about a high-level language we've worked on recently that appeared at PLDI this year called Dahlia, that is sort of a different take on HLS that gets rid of some of its sharp corners. I then, at the end, if I have time, we'll talk a little bit more about some ongoing work we have on developing an open source extensible compiler stack for languages like Dahlia that want to target hardware. But overall, our ambition knows no bounds, and we would love to reinvent the entire system stack, all the way from high-level languages to the actual hardware, in view of what programmers actually need in order to write effective software that uses FPGAs. So the first part of this talk is going to be about Dahlia. And to introduce you to the problems with HLS that Dahlia is trying to solve, I'm going to take you through an example of what it feels like to use existing HLS tools. The following analogy I've been told by many people doesn't make any sense, but I can't resist using it. It's that HLS feels like trying to turn a screw with chopsticks. That is, that you can sort of see exactly what needs to happen, but you're so far away with it that you don't have the control that you need to make that actually happen. I apologize if this analogy makes no sense at all. It makes sense to me, and so I can't resist including it in talks sometimes. So what we're going to do together is try to use HLS on this matrix multiply program. So there's you can read this C++, this C code if you want. It is, but it's not surprising at all. It's just the ordinary 3-loop nest that you might use to implement a matrix multiply. HLS tools will take a program implemented like this in C and generate working hardware for you, which I have to admit is a really astounding feat that it generates hardware that works at all. And the way it does this, as you might imagine, is by mapping constructs in the source language, like in C, to hardware structures that it generates. For example, these arrays that are declared at the top, those map into memories that get generated on the FPGA. Then there are operators in the C that get translated into functional units. And then there's a register, and then there are connections generated between the registers to make this work. All by itself, however, this initial version of the program is not terribly exciting because it's not terribly fast. The main thing that you can get out of using custom hardware, of generating an FPGA-based accelerator, is a lot of parallelism. So the main thing that you would want to do to make this an actually effective accelerator is to parallelize some part of it. That is, for example, we might imagine that this multiplication in the original C program, we would love to have not just one multiplier, but 3 multipliers that we run in parallel. In HLS tools, you can do this. You can ask for parallelism to be created, and you do that with one of these pragma annotations. This pragma HLS unroll thing does something that is subtly different from like unrolling in software compilers. It actually tries to run the copies that it creates of the loop in parallel. The thing that you might expect, therefore, in this is that the more that you unroll, the more of the FPGA's resources you take up in FPGA terms, the greater area that you use. However, in trade-off for using more area, the faster the overall matrix multiplication goes. I'm going to show you a few plots like this over the next little section of this talk, where the idea is that we're changing parameters, like I showed you on the previous slide, to vary from to try optimizing the program in different ways. And I'm showing you two different plots because these are the two figures of merit that matter when the main figures of merit that matter when evaluating these accelerators. There is the area on the left-hand side, which is the lookup tables or LUTs used. On the right-hand side, there's the runtime in actual milliseconds. That is how long actually executing this on the FPGA took. I want to emphasize that these numbers are taken from actual runs on a real FPGA in Amazon's F1 AWS instances. So these are not estimates, these are actual executions on FPGAs. So again, to emphasize what we expect to happen when we increase the parallelism using that unrolling thing, which is what's happening along the x-axis here, we're just increasing the factor in that unrolling pragma, we expect the area to go up and the runtime to go down. That is, we are trading off the area of the design for the performance. What we see, of course, is nothing like that at all. That is, that there is no clear trend here. And in the highlighted red case, in fact, it is perfectly possible to spend additional area to actually make your design go slower. So unrolling doesn't behave the way that we expect. And this is where the problems with HLS that Dahlia attempts to address stem from. That is that using an HLS tool, because it's a software tool and doesn't have awareness of, doesn't explain to the programmer how things are going to be instantiated in hardware, the programming model is fundamentally unpredictable. It's hard to say what's going to happen in the hardware when you change things in the software. So what's actually going on here in the hardware perspective is that when you ask for when you ask for the loop body, the multipliers to be duplicated, the HLS tool is faithfully following your instructions and indeed making multiple copies of the multiplier. However, it's not able to actually run them in parallel because there's not enough parallelism coming from the memories. That is, the thing that's actually storing the matrix can't feed those multiplies on every cycle. So what you need to do if you're an experienced hardware designer, you might be able to figure this out by yourself, is to partition the memories so they can offer more parallelism to the logic. So instead of silently generating these multiplexers, as the HLS tools does if you just unroll the loop, you also need to partition the memories into smaller banks so that they can feed the multipliers with sufficient parallelism. There is a pragma for that too. So if we go back to our source code, the way that you can rectify this problem is by partitioning each of those memories to a commensurate amount. That is, if you're going to unroll the loop 3 times, you would better partition your memories also 3 times. And here's where we start to see inklings of what's kind of going on here from a subtler programming language perspective. There is a underlying correspondence going on here between several parts of the program. That is, the loop that gets unrolled and the memories that are accessed from the unrolled loop have to have some sort of underlying correspondence. And if they do, then the parallelism matches up and you get the performance that you want. So it must be the case, therefore, according to what I've told you so far, that if we take this lesson, that is that we need enough parallelism from the memories to match the parallelism in the logic, we must be able to get good predictable performance out of this. So the next experiment I'm going to show you is doing the same thing, that is measuring the LUTs and the runtime of the accelerator while varying a different parameter. This time the parameter is going to control both the unrolling factor and the partitioning factor together. So according to what I've told you so far, it should be the case that now we can get more parallelism at the expense of more area and therefore get lower runtimes. What we see, and maybe you've predicted this, is not really that at all. There is a kind of clear trend going on in the runtime, but there's something going wrong with the area. That is, as we increase the partitioning factor, like generally speaking, we get more area, but it's really bumpy and we don't get the predictable performance trade-offs that we would expect. What's going on here is a different hidden correspondence. And this one is between the bounds of the loop and the unrolling factor. If you think about it, there's nothing really wrong with executing a loop in software in an unrolled fashion. That is, like, you just have to sort of skip one of the last iterations. But there's kind of a disastrous effect when you unroll a loop by an amount that doesn't divide the running time of the loop, that is the total number of executions of the loop, when you're generating hardware. That is, if there's just 3 copies of a loop, then it doesn't fit evenly into the 512 times we want to run this. And so a bunch of additional hardware, complex hardware, has to be inserted to accomplish this. And that can actually make the design larger and slower, even though you didn't intend it that way. So maybe this analogy makes a tiny bit more sense now. That is, there is something clear that you want to accomplish if you know a few basic things about hardware, but HLS makes it really hard to do that. And it sort of keeps you far away from the design you're trying to generate. HLS tools are remarkable tools. The fact that they're able to generate efficient designs from software that wasn't really even thinking about the hardware it was trying to generate is truly remarkable. But it means that when you know something about the hardware that you're trying to generate, it doesn't feel like a normal compiler. It feels like this enormous black box that you're sort of throwing a program into with a few hints about what you would like to get out the other side. And sometimes it works and sometimes it doesn't. The idea behind Dahlia, our programming language for rectifying some of these problems with HLS, is to bring predictability by constraining the language. So instead of letting you write any arbitrary C program you want, and then letting the HLS tool try as hard as it possibly can to generate efficient hardware from it, we're going to severely restrict the language to programs that we know have a predictable translation into hardware. So in a sense, this will make the language harder to use because there's only a tiny subset of programs you're allowed to write according to the type checker that we built for Dahlia. On the other hand, the way that we see it, it makes it much easier to use because now that subset of the language is far more predictable. It has a kind of direct correspondence to the hardware you expected to get out. So let me show you how this works in Dahlia with even more reduced contrived examples. Dahlia looks like this. Here's a little listing that declares a memory and then uses that memory twice. That is, on the right-hand side, I'm demonstrating the hardware that corresponds to this program in Dahlia. Dahlia, I want to emphasize, compiles to HLS C programs, but its job is to rule out the problems at the Dahlia level using a type checker such that you don't observe the kinds of unpredictability that happen when you write unconstrained C. The main question that Dahlia asks is whether parts of the program are allowed to run concurrently. In this program, we're accessing the same memory. That is, M1 here is a memory, and there are two different statements that are accessing it. One is a read and one is a write. The question that Dahlia's type system attempts to ask is this safe to do? In this case, it is not. The main problem that gave rise to all the problems to the unpredictability issues in the HLS examples from before is conflicting simultaneous accesses to memory. When it's not clear that what you're actually trying to do is physically impossible, that is use the same hardware resource, the same physical memory for two different accesses at once, then unpredictable things happen. The error that Dahlia gives you at this point says that the affine resource M1 is already used in this context. So there's a bit to unpack there. What exactly is meant by an affine resource? So Dahlia is an affine type system. Affine type systems have a lot of applications, but they sound a little bit funky at first. They're part of a broader family of type systems called substructural type systems, where the most popular standard bearer right now is probably Rust. The idea behind linear type systems and affine type systems, which are closely related, is that you are limited in how much you can use each variable, which by itself might not sound all that useful, but is what powers the ability for Rust, for example, to ensure that you free every memory that you allocate exactly once, and you don't use it after it's freed. We use the same kind of reasoning to build an affine type system for Dahlia that tells you that it's not legal to use the same memory twice in a context where that could happen concurrently. So this declaration here creates an affine resource that is something that is consumable when you use it once. And then these uses consume the permission to access that memory. So when we read from memory and we write to the memory, we potentially consume that memory and we prevent ourselves from doing it again in the future when that use might be concurrent. So that's why we get an error, as we should when we're trying to use the same memory in different ways in a way that's potentially concurrent. So this potentially concurrent thing is a pretty subtle aspect of HLS tools. It seems like these semicolons between the lines in ordinary language semantics should prevent parts of the program from running concurrently. And that's not what happens in HLS, and it's also not what happens in Dahlia. In HLS, semicolons, that is just the composition of statements, give permission to the compiler to try to parallelize in the best way that it can, up to the data flow limit. That is, like, we are not allowed to reorder statements where one writes to a variable and the other one reads from a variable. In Dahlia, we call the semicolon unordered composition. That is, we have to preserve the semantics of a sequential execution, but the compiler is allowed to execute these, to try to schedule these operations in the same clock cycle or in an unordered way. This is why we have an error when we try to use the same memory twice. Dahlia also has a second construct that's written like this with triple dashes that is meant to be very visually distinct from semicolons, which indicates ordered composition, which sort of means the same thing in terms of the sequential semantics of the program, but it requires the compiler to run those parts of the program sequentially. That is, read from the memory and then write to the memory. And for this, Dahlia is perfectly happy. That is, now you have separated those accesses to the memory in time, and Dahlia approves this message. So what's going on here in using ordered and unordered composition is a way to build up parallel programs in Dahlia while tracking the potential conflicts between them. So there's a building block that gives you temporal exclusion, and there's a building block that gives you concurrency. And using those, you can build up lots of interesting schedules and allow Dahlia's type system to check them for you to make sure that they don't have conflicting uses of hardware resources. I also now want to return to loops. We saw unrolling in HLS. Dahlia has unrolling too. There's a special unrolling keyword that you can put on for loops that says, make me 3 copies of this loop body and run them in parallel. And Dahlia, as you might expect, if you take this program that both reads from and writes to a memory and you try to run it in parallel, Dahlia tells you that that this is illegal because you're not allowed to use the same memory for reading and writing at the same time. Dahlia has banking, that is dividing memories into pieces. And this is the key to making programs like GEM, like the matrix multiply example I saw before, type check in Dahlia. The type of M1 and the type of M2 here encode information about this banking strategy. That is, they tell Dahlia that there's actually 3 affine resources available here for the program to consume. And so when we access it from a loop that's unrolled 3 times, there are 3 things to use, and Dahlia considers this okay because these accesses are going to multiple partitions. The key that makes this work is that there's information encoded in the iterator variable. That is, when we declare I here, that's not just an integer. It actually encodes information about the fact that this is in the context of a loop that's unrolled 3 times. So when we access a memory with I, we don't just want 1 affine resource, we want 3 affine resources to indicate that we want to access the memory 3 times in parallel. So it had better have sufficient parallelism available. This gets even more complicated when we look at nested loops. For example, the matrix multiply example had to deal with 2-dimensional arrays and therefore needed nested loops. By itself, this seems really hard to prove correct by the mechanisms I've shown you so far. That is, just saying that we're going to, we can, just using this like index math seems really hard to verify automatically using a type system as safe to parallelize. So Dahlia has a whole system that I won't be able to talk about in detail here, called memory views, that let you adapt the affine resources underlying a memory in such a way to let you access them in different ways. Overall this can work by this works by sort of simplifying the access logic and offloading reasoning to the type system. So by taking, for example, this suffix view of the memory, we can say that we are accessing it in a well-behaved way that is sort of like moving by a multiple of the banking factor of the underlying array. And then our access expression no longer needs to have that like funky indexing gunk in it. It can access it as something that looks to the type system like a normal banked array. And the ordinary, now we sort of like recovered the simple reasoning that the ordinary type system is allowed to do. That's all I'm going to tell you about the kind of the core of the Dahlia language. There's like a lot more in the PLDI 2020 paper that you can look up under the title Predictable Accelerator Design with Time-Sensitive Affine Types. And there's a whole bunch more in that if you are curious. There's like a lot more language features that I get to talk about. There's a whole bunch of other kinds of memory views and some interesting math underlying how those memory views work. There's also support for reductions through a different kind of language feature. If you're into this kind of thing, we also have a formalism and a soundness result. But the main thing that is relevant to us is whether this very restricted language that allows you to write a small subset of the programs that are possible in normal HLS still allows you to write useful programs. That is, programs you would actually want to write in HLS. Can you make good accelerators? So I'm going to show you an experiment we did with implementing a blocked matrix multiply. So yes, again, it's another matrix multiply. This one is different from the example I showed you because it's a nice, efficient blocked matrix multiply. And what we did is we took we did a design space exploration, which is hardware terms for trying out many different versions of the program with many different banking factors, many different unrolling factors, in an attempt to find the fastest possible variant of the gem. So I'm about to plot on these axes. On the x-axis, there's the performance. On the y-axis, there's the area. That is the lookup tables used on the FPGA. And good designs are in the lower left-hand corner. So in one of these design space exploration experience, you generally speaking have to explore a lot of designs. Generally speaking, you need to search this design space because the language doesn't give you direct feedback without actually compiling the program into what is a feasible or what is a well-behaved design. So we did this in the estimation mode of a commercial HLS tool. That is, unlike the previous plots I showed you before, these are not real executions. These are going through an estimator, which is pretty fast, but nonetheless took us 2,600 CPU hours of estimation time. So here's that space. Here's that design space that we explored. I'm highlighting the Pareto frontier according to multiple metrics on the FPGA. So this may not look exactly like a Pareto frontier on this graph because we're not taking the Pareto frontier with respect just to LUTs and performance, but also to other resources that exist on the FPGA. In any case, these are the ones that you would want to consider as possible design points for a well-behaved block matrix multiply generated by HLS. The important question for Dahlia, and remember this DSC I've shown you so far is just running on sort of unconstrained programs. The important question for Dahlia is whether it is possible to express most of these good, i.e. Pareto optimal designs in Dahlia without running afoul of its type system. So what I'm going to show you next is to highlight the points that Dahlia's type system accepts. So we took those same parameters and we fed them into Dahlia's type checker, and we classified them as either like Dahlia acceptable or not. Dahlia accepts only 354 out of the 32,000 points in this entire design space exploration. And we accept 15 of those 56 Pareto optimal points in the entire design space. Generally speaking, the ones that Dahlia does not accept, the ones that are Pareto optimal, but Dahlia nonetheless rejects, are ones that make somewhat questionable trade-offs. That is, spending a lot of LUTs to get a tiny bit more performance or vice versa. And if you look at the plot, you can see that we do in fact accept a large number of the ones that you would actually, generally speaking, want. That is ones on the lower left corner of the graph. So that's Dahlia. I would love for you to check out more about this. Richard Niggam, the main student who works on Dahlia, set up this really amazing interactive tutorial on the Dahlia website. So if you go to our lab page, again, that's capper.cs.cornell.edu. And if you go to /Dahlia, you will see this like interactive tool that lets you play with the language right in your browser. It is pretty snazzy. We're really excited about Dahlia, but I also want to tell you a little bit more about the rest of the story. We're currently in the middle of trying to take the predictability from Dahlia and to bring it to more of the system stack. So this isn't going to be the boil the ocean, solve the entire problem all at once project, but the next steps are to take this high-level language and explore its potential in a compiler infrastructure that takes us to lower levels of abstraction in the system stack for FPGAs. To motivate why I think we need a new compiler infrastructure for FPGAs, I want to highlight some of the differences in how it feels to program CPUs, that is to write normal software, from how it feels to program FPGAs. On CPUs, if you write hello world and you compile it, it doesn't take very long. That is, depending on the language you use, it might take around a millisecond. Compiling hello world for compiling a very simple design for an FPGA can take around an hour. Writing more complicated software and running it through the entire tool chain to run an FPGA can take hours or days. The reason for this is that the optimizations in the stack for FPGAs tend to be based on holistic meta-heuristics like simulated annealing that try to search for the optimal implementation of the program. Whereas for CPUs, we have gotten by with kind of best effort targeted passes that improve performance in small ways, but don't try to take the entire program and run a giant optimization procedure on it. Part of the reason that this remains how it is currently is because the hardware level resources that that compiler writers can target are exposed in the ISA for anyone to read for compiler writers to target. Whereas in FPGAs, the lowest levels of abstraction, that is the actual format of the bits that you stream onto the FPGA to make it do things, remain trade secrets. All of this all of this taken together, that is these parts, these contrasts between CPU and FPGA programming, I would argue makes sense for the old uses of FPGAs as circuit simulators and as prototyping tools for actual ASICs that you plan to manufacture in silicon. The reason is that the methodology that makes sense for circuits like that is inherently a waterfall strategy. It makes sense to make things, to make sure that your hardware is completely correct before throwing it over the wall to a tool that tries very, very hard to optimize it and as much as possible before giving you a final design. But that's not at all how most programmers are used to working with software. The way that I see this trade-off playing out between the hardware and the software communities when we're looking at compiler stacks is that the compiler stack for FPGAs has been prioritizing one thing over everything else, and that's optimality. That is, when you finish a design and you throw it over the wall, the tool had better try very, very hard to find the best design it possibly can to implement that specification. In software, that's not generally how things work. Yes, we care about optimality, we care about speed and performance, but those things are kind of balanced against other things that are equally important. Things like predictability, the problems that occur when software people interact with HLS tools, and things like debuggability, and critically, iteration speed. That is, we expect to be able to compile programs relatively quickly and run them and see what the performance is and tune them again. And all of this rests on kind of a culture of openness that more or less exists in the abstraction hierarchy for targeting software. In our lab, we sort of see it as an imperative to explore the potential for reinventing the system stack for FPGAs with some of these priorities in mind. That is, rather than letting optimality override everything, what if we prioritized the other features that people like about programming their software? It might be possible to generate better accelerators if the tool tries less hard to optimize your design and allows programmers more insight into the performance and lets them iterate faster toward a better design and a more correct design. So the way we see it is that we would love to reinvent a compiler stack for FPGAs that lets 1,000 flowers bloom, that opens up the abstractions between the layers in the system stack and lets all the tools that we like from software be ported over to the FPGA world, to designing hardware accelerators. To that end, the project we're currently working on in our lab is a compiler infrastructure that has the somewhat bold goal of being like LLVM, but for hardware designs. LLVM has a lot of advantages, but one of the big advantages that it had over prior open source compilers for CPUs was the idea that it could break up the monolith. That is, that prior compilers for CPUs, like GCC, for example, were so monolithically integrated that it was hard to make progress on individual parts. So even in the days before LLVM had like competitive performance to the code that GCC generated, its modularity was still an advantage. And this is what we're hoping to accomplish with a project called Futile, which is meant to sound hopelessly ambitious in building a compiler stack that targets this reconfigurable hardware. To illustrate that further, this is the shape of diagram that you might be familiar with when drawing the schematic for compilers and for LLVM in particular. That is, that the idea is to support not just a single input language, but a whole diversity of input languages, and to target not just a single backend, but a whole bunch of backends, and that these things should be mostly orthogonal. That is, there should not be too much n-squared reasoning between the input language and the target, and instead we should reap the benefits of a solid abstraction in between the front end and the back end of the compiler. This also enables the development of instead of having a single monolithic translation from an input language to the backend, we should be able to write small modular passes that it's possible to reason about the correctness and advantages of individually. And that all rests on having an intermediate language that works well for representing programs across the entire life cycle from front end to back end. One of the huge innovations of LLVM, for example, is that the intermediate language is intelligible to humans. If you dump it out to a text file, you can read it and understand the semantics of the entire program. And it's self-contained. That is, it doesn't make references to the original AST of the input program, and it doesn't depend on undeclared aspects of the hardware that it's targeted. So the semantics of the intermediate language are self-contained. And that's what we're aiming to create with Futile as well. In Futile, the key idea is to represent hardware programs along the lifecycle from front end to back end as a separation, as a sort of a combination of two important aspects. The structure, that is like the hardware-like resources and the connections between those resources in the hardware that we're generating. And separately, there's the high-level control, that is like things like while loops and conditionals, things that resemble something more like software. This kind of split representation, we believe, is the key to making passes modular and separating front ends from back ends. To show you a little bit about how that works, let's take this original Dahlia program. This is just a while loop that does an operation in some arrays. The Futile program, the Futile representation of this program splits apart the structural elements from the control. The structure includes those bits that I was drawing on the right-hand side of the screen in the Dahlia section. That is, things like memories and arithmetic operators and the connections between them. The control part looks more like software. That is, it says you still have a while loop. That is, we don't need to instantiate a bunch of counters, for example, just to generate a Futile program that implements a while loop. Instead, we can directly say that here's the structural elements of the program, and here is how they're controlled at a high level. Futile compiler passes, their main job in lowering to generate actual hardware is translating between these two worlds, and in particular, getting rid of control and generating structure. So iteratively, the Futile compiler takes elements from the control and implements them as structural elements. It does this step by step, eliminating more and more of the software-like semantics and generating components and hooking them up together to implement those semantics. We see this balance between structure and control as kind of like the underlying semantic concept that is necessary to enable innovation across the entire compiler stack, not just in optimizing programs, but enabling things like debuggers and more exotic transformations like super optimization. And we hope that this is the key that we need to bring things more into balance. Not to say that, that all future publications on FPGAs should happen in PLDI instead of ISCA, but there should be more balance. And we should be able to bring both software and hardware insight to bear. That's all I have for the talk. I want to emphasize again that, that all of the things I just inadvertently took credit for are actually due to a team of amazing researchers in our lab at Cornell, whom you can read more about here. I also I want to take this this opportunity while I have this platform to, because it's October, that a bunch of folks in our lab are looking for internships next summer. So if you are in industry and this kind of thing appeals to you, I would love to hear from you, and I will forward your job out along to folks in our lab. Thanks very much.
All right, thanks, Adrian. I will do the ritual single clap on behalf of the 65 people who are watching right now.
Thanks
great
so much,
talk.
Henry.
So I was actually at some conference virtually, and I don't know how they did it, but they played a track of like an audience applauding, and it was strangely super awesome, even though it was totally fake. So I need to figure out how to do that. Okay, so there's a number of questions. Let's start with the first one. Over the 80s and 90s, we had Dennard scaling that went along with the development of higher level languages, which maybe led to a de-emphasis on optimality at all costs. Is there a similar trend for FPGA hardware today?
Man, that's a great question. Yeah, that's a one of these like deep philosophical Moore's law style questions that is very fun to ponder. So yeah, so the hypothesis is that like the reason that we got JavaScript and Ruby and stuff in the CPU land is because performance didn't matter quite so much when we were on the exponential trend that Dennard scaling offered us. So what's going on with FPGAs now? That's a really, yeah, it's a thought-provoking analogy. And I think it would be hard to say that exactly the same thing is happening, because it is actually not true that FPGAs are getting, are like on an exponential trend to get like way, way better than CPUs. Of course, the whole reason that we were looking at FPGAs and exotic accelerators like that is because of the slowdown in advances in CPUs. But I wonder if there's some sort of like inverse trend to be mapped about how, as like pressure increases to like use a piece of hardware, then programmability becomes like begins to outweigh the optimality. Yeah, maybe is it Bobby? Maybe Bobby can get a law named after him about this.
The Bobby power law, if you will.
Yeah, right.
All right, sorry, Bobby. Okay, so the next question is from Shuwen Sun. So apparently some of his colleagues are feeling the pain of using C for programming FPGAs. I often hear the complaint about their C code working fine in simulation, but they behave differently on real hardware, which is something I think that you showed in the beginning of the talk. Does Dahlia or the new stack help with this kind of problem, or are we just not making it worse? I guess he means, are we just making it worse or just not improving the situation?
And this is also a super great question. So the first section of the talk was about kind of performance predictability, but I think that this person's lab mates is asking something even more troubling, which is about correctness, which is that like it's possible to write something that like, well, it works when you execute it, when you like compile it with GCC and you execute it on CPU. It also works if you compile it to RTL and you simulate that, but it does not work if you synthesize an actual FPGA bit stream and you put it in an FPGA and it computes just silently a wrong answer or deadlocks or something. This is a real fact of life. I can confirm that this actually happens. In the normal software land, we would call this a compiler bug. In the normal world of hardware, this is just like, for some reason accepted as normal. That is like, it's okay for like there to be subtle differences between the layers of abstraction. And I think that is just because it's incredibly hard to like make these things line up. That is like that even the difference between the semantics of Verilog and the actual execution of things on FPGAs is like, it has a lot of like weird caveats that like mean that, yeah, things are gonna differ quite a bit. And I really think that this is mostly an artifact of reusing the same kinds of tool chains that we have used forever to generate actual ASICs, where like you constantly have to be sort of doing what amounts to a best effort translation validation to make sure that every single layer continues to have the same semantics as you translate every single across every layer in the abstraction. To be honest, I don't know how to fix this. That is like, those abstraction gaps are so incredibly enormous that I don't know what the right approach is to fix this type of thing. However, I think we need to. That is, I think we need to treat them as compiler bugs and say that like, if you get the wrong answer after compilation, that's something that is on the tool developer to fix.
Right, that makes sense. So I have a follow-up question of my own. So, this is not a space that I work in, but this business of things, failing, I mean, there's some similarity to sort of undefined behavior in C compilers, right? Where the C language doesn't actually guarantee certain things. But it seems like basically everything is in effect undefined behavior because of races, right? Like that's what's happening here. So is it that there's not any tool support at all to help the programmers who are not, I mean, Dahlia is brand new, they're coping with C and doing HLS. Do they just literally go and ship this stuff and have it get baked onto an FPGA and then discover the errors later? There's no tooling support to help them?
Well, there are tools in the sense that there are multiple levels of simulators. So this is the best that you can do, is that you can do like what is sometimes called software simulation, which actually just means compiling to RTL and then simulating the RTL, and that can catch a lot of bugs. However, even doing that is pretty rough. That is, if something goes wrong in the if there's just a plain old HLS compiler bug, which exists, like understanding what went wrong by debugging the RTL is sort of like stepping through the assembly of your program without debug symbols. So that's possible, and people definitely do it, but there's not a lot of support beyond that.
Got it. Okay. Yeah, sounds grim. All right. So we have another question. We still have time for a few questions, which is good. So there are different DSL implementations that target FPGAs, specifically, for example, for image processing or for DNNs. Have you implemented the code generated by some of these DSLs in Dahlia to see if they're correct according to Dahlia's type system?
That's a super interesting question. So yeah, right. There's a really a surge towards DSLs to target hardware, which is for obvious reasons. And some of those generate RTL themselves, but some of them generate C and feed them into an HLS compiler to generate the final result, which again makes sense because it's a massive shortcut over generating RTL. The answer is absolutely not. We have not tried like taking the generated C and then converting it to Dahlia to verify that it is like correct according to Dahlia's semantics. It'd be super interesting to do. More pertinently, however, to shamelessly market our future work, the idea behind Futile is to make it easier to not have to go through an HLS compiler. That is, that the languages of the future that are trying to do image processing or whatever and trying to generate an FPGA accelerator shouldn't need to generate C source code and rely on all the problems in HLS compilers. They should generate Futile instead and generate RTL that way, which we hope to be like much more predictable and much more debuggable.
Sure, sounds good. That makes a lot of sense. So quick question, let's see. So there's a follow-up to this. How hard is it to port an existing complicated program to Dahlia? Do you have any experience? Like what's the largest program that you've created or ported over to Dahlia? Maybe that would provide a sense of scope. To
be perfectly honest, the programs we've written in Dahlia have all been really short. That is, like they're in the order of hundreds of lines. So there's no like massive program that has ever been written in Dahlia. The reason for this is that Dahlia is for writing is intended originally for writing these individual computational accelerator blocks rather than porting Doom, for example, to an FPGA. Yeah, so like I think there's a broader question here about what is the right like scope for hardware accelerators. Like what is like at what point are things complicated enough to make an impact in the real world performance of software? And I don't think that humanity has a great answer to this question. That is, like, in general, like what is worth accelerating? Because like if your aim is to accelerate machine learning, for example, it is entirely possible to fill up an entire FPGA just doing excellent matrix multiplication. So like it is valid to consider matrix multiplication a complete program in the acceleration domain. Of course, there's like a lot of other stuff in machine learning too that's not just matrix multiplication. So like, should we try to run all of TensorFlow on an FPGA? Is that like within the appropriate level of ambition for hardware acceleration? I honestly don't know, and I don't think the community has an answer yet.
So I'm going to jump ahead to a question that I think is somewhat related. So Microsoft, as you of course know, uses FPGAs in their data center as part of Project Catapult. And the questioner says, for many applications, I'm not sure how many. But for some, for sure. Any thoughts or ideas on how they overcame the problems with programming FPGAs that you described? Do they use proprietary tools? So I'm not sure how much you would know about what the internal goings on are of Microsoft, but if you have some,
I have no inside information into this. However, there's a really exciting development that there are rumblings and some public evidence that that Microsoft is working on their own like language in the ballpark of Dahlia. And by that, I just mean something that is not C, but is also not RTL, that is meant to make you more productive when you're designing hardware. The language is supposedly called Sandpiper. I know this from Twitter, not again from any inside information at all, but it indicates that that folks inside Microsoft are indeed working on language tooling to make designing FPGAs, designing FPGA-based accelerators better. However, I think my actual answer to that is that it is the case that like until this new language tooling was developed, people wrote Verilog, and they are amazing. They're like really excellent RTL designers that work in that team. And it is like to the awe of everyone that they're able to accomplish what they have done. And that's super great, but it also sort of, I'm sure to everyone involved is not a surprise that we need to sort of lower the barrier to entry so that these like truly amazing RTL designers at Microsoft are not the only people who can write this type of accelerator.
Sure. Yeah, it's, I mean, obviously if you're a large company and you can afford to hire amazing RTL engineers, this is sort of like game developers if they can hire an amazing game developer, they can do all of this stuff, but that doesn't mean it's easy or that everybody can do it. So, so great point. So let's see. So I'm just gonna pick one question. Somebody asked two, but I'll pick one of them. Let's see. I feel like that must be required. So seems like unrolling is a key part of Dahlia. What kinds of standard unrolling does Dahlia support? Would they unroll loops whose bounds are unknown statically?
Yes, the bounds do not need to be known. The amount that you're unrolling does need to be known. And yeah, right. So the point is that we do a very straightforward kind of unrolling, which is take the loop body and duplicate it n times and run those things in parallel. So this is not full unrolling, as you might think of it, as sometimes people call this partial unrolling, because it's not unrolling to the loop bound.
Okay, great. Let's see. So a couple small technical questions. So one is, Dahlia is a high-level language, so Dahlia code is converted to RTL, not binary streams that FPGAs need. Is that accurate?
This is correct. Okay. In fact, the current version of the Dahlia compiler generates C, just like those image processing DSLs we were talking about before, and feeds it through an HLS toolchain. We have a implementation of the Dahlia compiler that targets Futile instead, and therefore doesn't need HLS. But that is not what's reported in the PLDI paper. Got
it. The second one is, this is maybe a philosophical question. Is Dahlia like CUDA? Oh, I see where the questioner is going. The question is, some parts are executed on a CPU while other parts are converted into hardware circuits. So I think the question is this sort of like dual mode. Does Dahlia support programs that run partially on an FPGA and partially on a CPU?
Right, and that kernel annotation in CUDA is the kind of the operator part. Yeah. The answer is no, it's not like CUDA. It is only for the FPGA part of the program. Personally speaking, I think this is a super important problem all by itself. That is, like, if imagine that you are not in the business whatsoever of being a like hardware accelerator compiler person. There are still super interesting research problems to be done here, just about the interaction between the CPU and like whatever language is going on in the FPGA, about sort of like managing the data movement between them. We have not solved any of that in Dahlia. I hope somebody works on that. That would be awesome.
So let's see, maybe somebody in the audience will. So let's see, I'll just go in order. So there's a question, Dahlia constrains the search space with a typed language, but I guess the argument is somehow this is a burden on programmers. Why not let the programmer write arbitrary codes, I guess they mean typeless, and let a compiler take care of the optimal design without these kind of type system that you all put in place? Yeah, well, sorry to be blunt, but that's exactly what HLS does. That is, C is a typed language. There are types in it, obviously. However, it doesn't constrain you to anything that is like actually possible to implement in hardware. And so this is the kind of trade-off I mentioned briefly when I said that Dahlia simultaneously makes things harder to use and easier to use. That is, it makes things harder to use because you can't write whatever program you want. However, it makes things easier to use because it gives you actionable feedback to understand why your program might not perform as well as you want it to. I believe this is the right trade-off. I like, just as with typed and untyped languages in software land and the varying levels of performance you get out of software languages, I think it also makes sense to have like totally unconstrained programming models. Sometimes it like generate whatever hardware and sometimes it's terrible, but that's not our business. Right, yeah, I mean, I think the notion that the C that one uses for HLS is full C in all of its glory is also that's just not true, right? You can't write an arbitrary C program and hope that it will compile it to an FPGA. It's always some sort of subset. So the type system is just imposing more structure. And you can't do everything. Open on an FPGA, for example, I guess. Yeah. My favorite example, of course, is malloc, or recursion. Do both. So let's see. So here's another question. So this is about really a paradigm. Does Dahlia support programming with an event model? So the questioner notes that they've had experience with Verilog and finds this paradigm is more suitable for working with devices with serial execution because it's more convenient instead of polling and so on. So I'm not sure this is something that that your language addresses, but how about it? Yeah, it's an interesting point. Like by event model, I'm guessing that the question asker is imagining something sort of more like a data flow programming language. That is to say, like something that says you make like a bunch of nodes in a data flow graph and you sort of fire whenever your inputs are ready. And indeed, this does have like a lot of good analogies to generating actual hardware. So I think there's absolutely nothing wrong with that, and it totally makes sense. And like the question asker sort of put it, it might make sense to have something more program countery, more von Neumann looking like Dahlia in some parts of the program, but then like to organize blocks of Dahlia programs in kind of a data flow style. That might be an interesting approach. Like I guess part of the message that I hope people take away from this talk is that there are lots of potentially very interesting designs of languages to target hardware that are out there. There's like lots of great creativity is like waiting to be unlocked
in inventing new languages that like faithfully represent hardware semantics instead of just porting over old software languages, like something more data flowy. And those things generally do not exist right now. There's not a lot of programming languages diversity in generating hardware. So if you find that kind of thing exciting, I hope that you do it, and I hope you use Futile as your compiler infrastructure.
Excellent. All right, we'll take one last question. So the question is, since FPGA compilers have bugs, how can we quickly know that the FPGA is actually doing what the program was intended to do?
I don't know if you can. It's like, at least in the status quo, you like, even just getting like, I can tell from very painful experiences in the past, just trying to get your thing to execute on an FPGA is a huge burden. Trying to see if it executed correctly, that is like getting the answers off of the FPGA and comparing that to like an execution of a reference implementation is also a huge pain. So more detailed tools for understanding what went wrong when the answers are wrong on actual FPGA executions is in my view, a giant unsolved problem. There's a lot of work out there in like verification, just ordinary hardware verification, but in the domain of building computational accelerators that run on FPGAs, it's a kind of a bleak scene.
All right, on that happy note, we'll conclude. Well, you're here to save us from the bleakness, so that's the happy note. All right,
exactly.
Great. All right, so I'd like to thank you again for your great talk and for all the questions. Adrian has said that he'll be available in Slack to answer questions offline after the talk. So thanks again. Thanks to everybody for attending, and hopefully see you all next week.
Totally.
Bye-bye.
Thanks, everybody. I really